Okay, 9.3 is all triangles. It's the geometry of triangles. And so if you ever had a high school geometry class, this was a huge part of that class. Proving congruency between triangles is where you first would have encountered proofs. If you ever have done a proof, what happens is you have a 2-column side-by-side where you make a statement and then you give a reason why that's true. How do we know that that's actually true? And we're going to be using the 2-column method today to prove congruency and similarity between triangles. So this symbol up here, the equal sign with the little squiggle over it, is congruency. So triangles that are congruent, there's that information down there. Triangles that are congruent are the same size and the same shape. They're identical. So the blue and the red up here, or the first two on your handout, notice they have the same tick marks in the same spots. They have corresponding angles. Everything matches up. So we can confidently say that triangle ABC is congruent to triangle DEF. But that's a lot of information that we have to have. If they are different sizes, even if they're the same shape, they're not congruent. If all the angles are the same, but the sides are different, they're not congruent. You have to have all of it to be the same triangle. And so there are congruency properties that we're going to learn that are going to help us to prove that two different triangles are congruent whenever we're not given all the information. And so these in this first box are super important. And if you had geometry in the past, you will have seen these at some point. The first one is side, angle, side. And these shorthand versions next to it are usually how you're going to reference them after you get used to them. But side, angle, side states that if you have two sides and the included angle between them of one triangle is equal to another, then we can say that the two triangles excuse me, are congruent. So if I know that side DE is congruent to side AB, and I know the angle here, E and B are the same, and I know B and C are the same here, I can deduce from side, angle, side that the two triangles are equivalent. Even if I don't know what angles A and C are, even if I don't know the measurement of side AC. With just that information, I have enough to go off of. If I have angle, side, angle, I can make the same conclusion. So if I know angle D and the side between them and angle E corresponds with A, the side, and then B, I can deduce that my two triangles are congruent. And the last one is side, side, side. If all three sides of a triangle are equal to a corresponding triangle, then I can tell that those two triangles are congruent. You may be looking at this and thinking there's a couple of different patterns that are missing. I can't have side, side, angle and deduce that I have congruency. Another way of putting that, I don't have any ash triangles where I have angle, side, side. It does not work. It does not guarantee congruency at all. So side, angle, side does congruency. Angle, side, angle does congruency, and side, side, side will do congruency. And so when we're going to prove congruency, these are the things we're going to be looking for. What do we know about our triangles? Do we have any of these that are going to come into play to help us prove congruency? I need to put another sheet of paper under there, but here's your first style of problem. It tells us we're going to prove congruency, and it gives us a picture. And it's a weird looking picture. I'll just be honest. It looks more like a bow tie than triangles, but hopefully you can see the triangle. And I didn't label all of it. There's supposed to be a C in there. This is a C up here. But hopefully you can see that we do have triangle AB or AEC, this left one, and we have triangle EBD over here. Yes, they cross. and that's okay. What we're trying to prove is we're trying to prove that triangle ACE is the same thing as triangle BDE. And the only information we have is we have this picture and we have the given information that they actually will give you. They will list out the given information, or at least some of it, that they really want you to pay attention to. So they're giving you that side CE, that's this one with the 2 tick marks, is the same measure as side ED. And that's what the 2 tick marks are telling you. The sides with 2 tick marks are equal. Side AE is equal to side EB. Whoops, sorry, I bumped it. Now that's all they're giving us. We have these 2 different sides. We know they have the same measure, but somehow we are going to have to prove congruency between these. And so I'm going to show you how to lay out a proof and what's going to be expected as you move forward with these. So I will have to slide up, but I'll slide back down for the others. When you are doing a proof, you will have 2 columns. So think of like a T-chart. One side will be your proof. One side will be your reasoning. The way you want to start your proofs is you always want to start with the stuff they give you. What do we know for a fact? Well, the first thing I know for a fact is I know that CE equals ED. And I even label my points so that I know this is one reason, or this is one proof, and here's my reason for it. It's given. That's something they told us. Another point is that AE equals EB. That's given to us. Now, that's the end of the information that's given to us. We have to be able to come up with more, because having 2 sides equal does not guarantee congruency. Who wants to take a guess at what else we can prove based on the way this is drawn in these different triangles? Okay. What type of triangle do you think it is? And does that help with proof congruency? Okay. We don't know that, though. Bless you. We know it's not equilateral because this side has 2 tick marks, this side has 1. But that doesn't help us prove congruency. To prove congruency, we either need to have angle, side, angle, side, angle, side, angle, or side, side, side. So right now, we have 2 sides. So that's probably telling me I'm not going to use angle, side, angle. I'm going to either use angle or side, angle, side, or I'm going to use side, side, side. So side, 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 I'd have to be able to say absolutely that side AC equals side BD. I don't really have any way to prove that at this point. I'm not going to take a ruler and measure it. That's not how we do this. So I need to be able to prove that the angle that lies between my sides, this angle in here, has the same measure on this side as it does over here. Because if I can do that, I will have side, angle, side. How can I prove that these 2 angles are the same?
Line AB and line CE cross at one point. So that would make it the thing we did before, an intersecting line.
Okay. So that makes these 2 angles what? There's a special term for what these angles are. Because we're trying to prove that angle CEA is equal to angle DEB DEB. And from, I think, 9.1, we have a special name for what these are. What did you say?
Alternate interior angles?
So alternate interior angles deals with transversals. And we're not guaranteed transversals here because we have to have parallel lines to have transversals. So maybe something that came before we talked about transversals. Maybe something starts with a V. Close. Kind of sounds like that. Vertical angles. Vertical angles are always equal. These are vertical angles. So, don't let the stuff from 9.1 go away. It will come back, especially in this chapter, or in this section, because we have to use that information. All the stuff for transversals will pop up here, just not yet. So they gave us a side. We just proved that the angle in between our sides is congruent. And so right there we have side angle side. So we can conclusively say that triangle ACE is congruent to triangle BDE. How do we know that? Because of side angle side. And in 4 steps, we have proven that these 2 triangles are the same. They have the same measures. They're congruent. But this is the layout that you need to use. Excuse me. Write down what they give you, and then think about what else can you deduce logically. I couldn't say these 2 sides were the same based on what I had, because I didn't know anything about those 2 sides. I couldn't say anything about the other angles necessarily yet, because I don't know if these 2 lines over here are horizontal, and thus I do have transversals. If I know that those are parallel lines, then I can use all my transversal stuff, and that makes it a little bit easier. But I had to use what they gave me, and they gave me 2 side lengths, and so I needed to either prove the other side length or I had to prove this angle. Let's do another one. This one looks a little bit like a parallelogram cut in half. We're going to prove congruency again between basically like the top right triangle and the bottom left triangle. So they give you a picture. And then this time, they're not telling us any side lengths. They're telling us the measure of angles. They tell us that the measure of angle ADB, that's this top left, is the same thing as the measure of CBD, that's over here. It only has 1 arc in it, and so those correspond. The other arcs, there's 2 in each corner. That's telling you those correspond. So the number of tick marks will correlate, or the number of arcs will correlate. And they want us again to prove that these 2 triangles are congruent, which means we either have to prove side, angle, or side, side, side. And just like with the last one, I'm going to start by listing the given. The reason why I label mine like 1, 2, 3 is so that when I'm looking over at the reasoning, I know exactly which reasoning goes with which step, and it doesn't leave me to second guess anything. Dang it, I wrote that again. D, B. We have 3 congruency properties. We have side, angle, side. We have angle, side, angle, and side, side, side. They gave us 2 angles. So let's logically assume we're probably going to use angle, side, angle, because that lists 2 angles, as our main reasoning at the end. So if we're trying to prove angle, side, angle, side, angle, we have to prove that this is the same for both triangles. Can you confidently say that side DB is the same as side BD? Hopefully you guys are thinking, oh my gosh, yes, this is stupid. Because it's obviously the same side, right? Okay, I'm not trying to trick you. It really is obviously the same side. So the way that they have it put, and one of the reasons why I included this problem is let me put it over here, side DB equals side BD. The reasoning for it, and this is why I wanted to include it, is they call it the reflexive property. And if I didn't include that as an example, then you wouldn't know the reasoning behind it. So reflexive property, aka it's a shared side. But the mathy way of saying it's a shared side is saying reflexive property. So that's the important part of this one, reflexive property. With that one statement, though, we have officially proven that triangle ADB is congruent to triangle CBD. Why? Because we have angle, side angle. Do note that the side had to be the side between the angles. I couldn't say that this side out here worked because then it's not a shared side and it wouldn't prove congruency. It had to be the side in between my two angles. You want to do another one? Yes, of course you do. Sorry, I'm going to try and save some paper, so I'm turning sideways. We're going to prove congruency again. This will be our last congruency one, and then we'll prove similarity. So here's our picture. We're going to have a big triangle. We have a line running down the middle. This is A, B, C, D, line, 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 line. And actually, I'm going to leave it like that. I know in Pearson, they usually write out all of your given information, but I want to see if you can tell me what my given information is. Because honestly, you're writing that information twice anyway, so. This time you're only going to be given a picture with all the tick marks. We have to prove congruency, so our end goal is to prove that the triangle ABD is congruent to CBD. So the first thing I want you to do is I want you to give me something that the picture tells us for fact. Do what? Okay. What about it? Okay. So we know that the side BD equals DB, just like on the last one. Why? Because of our reflexive property. So that's not actually our given information, but I will take it. It's definitely something we need. We need to know that this side is going to be the same for both of our triangles. And I'm putting 3 tick marks on it because I cannot tell you that for sure it's the same length as one of the other sides. All right, give me another thing we know about this.
Line AB equals line BC.
Okay. AB equals BC. How do we know that?
The tick marks.
Yep, it's a given. So our picture shows us this with the given information. We didn't have to logically come up with it. It was already marked for us. So what else do we know? AD equals DC. Again, that's given. So can we confidently say that triangle ABD is congruent to triangle CBD? That's a 4.
Side, side, side.
This one obeys the side, side, side. This side's equal to that side, this side's equal to this side, and this side is obviously equal to itself. Thus, we have 3 sides of our triangles that are congruent to each other, so we can say they are congruent. So we did one of each type is basically what we did. We did a side angle side, we did an angle side angle, we did a side side side. Are there questions on any of these, how we're using the information they give us, or anything like that? Okay. Here's some important things about isosceles triangles. Isosceles triangles are the triangles where two sides have the same length. It's these two right here, and this bottom one would have a different measure. So if you have an isosceles triangle, which is the big one, ABC, then that means that AB equals the same measure as CB. And if D ends up being the midpoint of our base, then we can say confidently that these two sides are the same. And after that, we can make a lot of conclusions. We can say the base angles, A and C, have the same measure. We can say that triangle ABD, that's this top one, has the same measure as the triangle CBD, which is this top one. And we can say, because this is going to be bisected by a perpendicular bisector, that these two angles in here are 90 degrees. So that's a lot of good information. Do you have to memorize all of that stuff? No. It's just really nice reference so that when you're dealing with an isosceles triangle, we can actually make a lot more conclusions based on less information, because all isosceles triangles work the same way. They all are going to obey these nice rules. So that's why I give you a picture. That's why I give you that table. Let's talk about similarity. Congruency is where our two triangles are exactly the same. Same size, same shape. Sure, you could turn one a certain way, but everything matches up. Similar triangles are different. They have the same shape, different sizes. Similar triangles have the same shape, but different sizes. So I know yours are not colored. We don't have a color copier downstairs. But hopefully they're different enough that you can tell which ones are supposed to be paired. And then obviously right now you can see the colors. These two are similar. Same shape, different sizes. Same thing here. Now, the green ones, these last ones, they look like they very well could be congruent. They may be the exact same shape and the exact same size. If you are congruent, you are similar. You're just not very interesting that way. If you are similar, congruency is not guaranteed at all, because these aren't the same size. These aren't the same size, and these may not be, although they look like they are. So for a triangle ABC to be similar to another triangle, both of these conditions must hold. The corresponding angles must have the same measure. So all of your angles have to be equal to their corresponding representative. And then the side lengths have to have a common ratio, aka they must be proportional. So if I'm going from the little blue triangle to the big blue triangle, in order for these to be similar, it has to go like I'm doubling the side length to get there, or I'm halving the side length to get there. There has to be a common ratio to hold. And as long as both of those two things work, then we're going to have similar triangles. Similar triangles don't have as many, like we had 3 congruency properties, we don't have as many for our similarity. Really, there's only one additional one. But if all the angles have to be the same inside of our triangles, then really we have similarity if we have angle, 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 and we can prove that proportional setting. So let me write down the problem, and we will do a similarity one. So similarity, we will have a squiggle in between. We will not have the equals. And I'll show you that. We're going to prove similarity. And we're going to be given the fact that AB is parallel to ED. If you see that as ever one of your given statements, it's a good idea. You're probably going to be using some of your transversal information. So you might want to get your transversal stuff out from 9.1. And we need to verify or prove that triangle ABC is similar to triangle EDC. And this picture is going to look pretty similar to the first one. We just don't have the same given information, so we can't make the same logical conclusions. I don't know if you can see that. So let me slide up. But very similar picture. But notice there's no tick marks anywhere. We don't know the measure of anything to be the same, at least not given to us. The only piece of information that we have is that side AB over here is parallel to side ED. And when we have two lines that are parallel to each other that are cut by either a single line or two lines, it's a transversal situation. It's just we dealt with our transversals. Watch out, I'm going to turn it. We dealt with our transversals like this, where we had our horizontal lines running like this, and then our transversals cut through like this. We did a really big problem that looked really similar to this, where we had to find all 10 of those inside angle measures at the end of 9.1. We're still going to use a proof. We're still going to use our two-column system. But in order to prove that two triangles are similar, we have to prove that all the measures are the same, and then we can prove that they're similar. So let's do it. Our two-column, our proof, and our reasoning. And I'm going to start with what they give me. They only gave me one thing. They gave me that AB is parallel to ED. So we really need to prove that all these angles match up. Which angle stands out to you first is the easiest one to prove. And that's kind of arbitrary because what's easy to you might not be easy to the person sitting next to you. Let's start with, let me give you a helper. What can I say about angle ACB? What is that equal to? So angle ACB, that's this one. DCE. It's going to be equal to this one. Why? Vertical angles. Okay. That one's kind of the easy one. That's usually the one that I look for first, is if I look and see, are there any vertical angles? So I got one down. So then if I think about this being horizontal lines that are cut by a transversal, kind of ignore the other one for a minute. So I have this one here. Vertical lines cut by a transversal. What can I say about this angle up here? The measure of angle BAC has to be equal to what angle over in this triangle? CED. Why? We have to have a reason. I don't know, you tell me. What kind of interior? Because we had a couple. You're right on which one it matches up with, though. These are alternate interior angles. Good job. Alternate interior angles are always equal. I didn't bring my 9.1 to show up here. But that table that has all of the, there's a table that had 4, the alternate interior angles, the alternate exterior angles, same side interior angles, and I don't remember what the 4th one was. What was it? corresponding angles. That's right. Okay, so far we've proven 2 of our angles, so we need to prove this last one is congruent to this one. We need to prove that angle ABC equals angle EDC. How would I know that? How did I know that angle BAC, that's this one, was equal to the CED down here, or D's? Those were alternate interior angles. What are these? They're alternate interior angles. We just have 2 transversals going on here. We've got this one that's a transversal, and we've got this one that's a transversal. These are still alternate interior angles. You can have the same reasoning for more than one piece of information. So we had vertical angles, 2 different pairs of alternate interior angles. With that, though, we have proven that all the inside angles are congruent between the 2 triangles. So I can say with confidence that triangle ABC is similar. I can't say it's congruent, but I can say it's similar to triangle EDC. Why can I say that? Because we proved that all of the angles are equal. So angle, angle, angle. This one was a little harder because it didn't give us anything. All it told us was we had a set of parallel lines. So if you ever see parallel lines, pull up the transversals. You're going to have some of that information that's going to come up. With this information, we couldn't have immediately pulled out congruency. We just don't have enough information. Having all the inside angles be equal doesn't guarantee congruency. Okay. There is a angle, just 2 angles, similarity property. It says if the measures of 2 angles on one triangle are equal to the measure of those 2 corresponding angles on the second triangle, we can actually stop there and say that they are similar. So on this proof that we just did, we found all 3 of our angles. But really what it's saying is we could have stopped and we didn't need to figure out this one. And that's because of the rule where our interior angles have to add up to 180 degrees. And so if we've already proven 2 of them match, the third one is going to have to match because there's nothing else that would add up to 180 degrees, so it wouldn't work. So really when you're proving similarity, as soon as you prove 2 of the inside angles are similar, you're done. You don't have to go looking for that third one. You don't have to argue for it. And so that's kind of nice having the angle-angle similarity property. Cuts our work down a little bit. All right. I've got some problems for you. These ones are different because these are not proofs. This is just going to be a work it out problem. Sorry, you can't see any of that. Let me not do that. All right, there's that. They're going to tell us that we have triangle EDF, and it is similar to triangle CAB. It wants us to find the missing sides of triangle EDF. And here's our triangles. These problems where we have similarity between our triangles, they can be word problems where it's talking about the shadow that a person makes on the ground compared to the shadow that a flagpole makes on a ground. Those are similarity problems. I promise when I write stuff, it doesn't look as crooked on my paper. So these are our 2 triangles. They're obviously different sizes, but they are generally in the same shape of a triangle. They do tell us that they are similar. So if I know they're similar, that means I know all the inside angles are the same, the corresponding angles are the same to each other, and I know that there's going to be some form of a ratio to tell me the difference in my sizes of their side lengths. Now, some of them are a little bit obvious where you can deduce what that ratio is. But I'm going to show you how we do this if we don't know what the ratio is. I'm going to assume we can't figure it out just by looking at the picture. Notice they give us all the sides on one, and they gave us one side on the smaller one. And what we need to find is we need to find what is this one and what is this one. So we're going to use the information of our bigger triangle to help us. Okay, what we know is I know that this side over here correlates to this side over here, right? Because they're similar. So I know that 8 correlates to 16. That's this side to this side. And if I'm going to set up a ratio, I'm going to set that equal to, I don't know what this one is, the EF. So I'm going to call that one EF. But it correlates to 32. The big thing here is the same things go on top and the same things go on bottom. So both of the measures on the top come from the same triangle. Both the measures on the bottom come from the same triangle. If you were to flip this, it does not matter. But what you don't want to do is I don't want to have small triangle, big triangle, small triangle. That'll mess it up. So you have to stay consistent in that if I start with a small triangle on top on the left, it's got to be the small triangle on the top on the right. Now, how do we solve? What's the nice method that we have to solve when we have a fraction equal to a fraction? Cross multiplication. That's exactly right, or the butterfly method. Some people may know it. Cross multiplication. We take the top left times the bottom right. So we'll take 8 times 32. 8 times 32 is 256. And we take bottom left times the top right, giving us 16EF. If you don't want to write it as EF and you want to call it X or something like that, you totally can. I like leaving it as EF so I know which side I'm actually talking about. To solve, I would divide both sides by 16. And I find that 16 equals EF. So that's this side measure. So to find my last one, I could do the exact same thing. I can even keep my first fraction the same. I can have 8 over 16 equals, but this time I'm talking about DF. And what does DF correspond to? Yeah, to 24. It corresponds to side AB. So then when I do my cross multiplication here, taking 8 times 24, which gives me 192, and 16 times DF. Whoops, that's not equals, that's DF. Divide both sides by 16 yet again, and I find that DF is 12. I show you the cross multiplication way simply because sometimes the ratios aren't nice. This one had a ratio of 2. And what I mean by that is I can see that when I go from my large triangle to my small triangle, I cut it in half. So I could have just done that for all the other sides and not done the cross multiplication. 32 divided by 2 is 16, 24 divided by 2 is 12. But if we don't learn it with the cross multiplication method, then we won't know how to do it when it's not obvious what those are. Because not every ratio is going to be a nice number like that. Do we have any questions on this? On how we do these? Okay. There is a problem. I'm trying to figure out that we're going to skip. It's in my notes. It's the next example that would be in my notes. The only reason we're going to skip it is based on time for today. It's because it's a long one. Again, we have 2 triangles. They tell us they're similar, but they want us to find all the missing parts. So it's not just about finding the side lengths. We also have to find all of these angles. So remember, if you're a similar triangle your side lengths are proportional. And this is one that, see, this is why I like to show it with cross multiplication. I don't know what I'm doing from 144 to get to 48. I don't know what I'm multiplying by or dividing by to get there. And so I would set up a ratio, again, and I would find these side lengths. But when we are dealing with similar triangles, the inside angles that are corresponding are the same. So there's actually not anything for you to do. If you know that this angle is 52 and this is its corresponding, we know what this one is. But the way that I would approach this problem is I would list out every piece of information for my two triangles. I listed out my three angles for my STU triangle, and then I listed out my sides. Then I listed out every angle for my XYZ triangle, and then I listed out their sides. And I listed them out so that they would be corresponding. And then what's next to them in these little parentheses is really just me telling you where I got this information. It's given to us, or I found it using the inside angles, have to add up to 180, or I knew that it's similar to this other angle in the other triangle, and so I know it from there. And so all of this is in the handwritten notes. And if I need to go into it a little bit further in an email, or if I need to make a little video working through one of these, I have no problem doing that. But all of this information is here. I'm letting you see it for a second, and then I want to make sure we talk about the Pythagorean theorem before we are done with time. The Pythagorean theorem is the last box on the little handout. The Pythagorean theorem is actually what the Scarecrow misquotes at the end of Wizard of Oz. If you listen to it, he says isosceles triangle because isosceles sounds more smart than right triangle, and so he actually gets it wrong. So he hasn't quite obtained all of those brains yet. But the way that the Pythagorean theorem works is that a Pythagorean theorem works for a right triangle. A right triangle means you have a right angle in there. The side that is opposite your right angle is known as your hypotenuse. And then the others are just side A and side B. If you take the measure of side A and the measure of side B and square them and add them together, you will get the side of the hypotenuse squared. So A squared plus B squared equals C squared. This is a really huge theorem that will continue to pop up in math, especially geometry and trigonometry. And it's going to pop up in your problems today. You have at least two homework assignments or two homework problems where you deal with this. And we're going to do one of them quickly because it actually is a quick one. I'll leave the Pythagorean theorem up there for you. It's telling us to find side A. And then it gives us a nice picture. We have a right triangle. We have side A. We know 39. We know 36. And that's all it gives us. But since it tells us it's a right triangle, I can figure out what side A is using my Pythagorean theorem because I know A squared plus B squared equals C squared. The most important thing you have to remember is your C is always opposite the corner. It's opposite your 90 degrees. So I'm going to plug in these values. I don't know what A is. That's what I'm figuring out. My B is the side that's over here. So not the C. It says 36 squared equals 39 squared. These are obviously a little bit larger numbers. A squared plus 36 squared is 1296. 39 squared is 1521. I'm going to subtract the 1296 over. So I have A squared equals 225. Now the question becomes, how do I figure out what A is? You square root it. To get rid of a square, you have to square root. But if I square root the left side to get rid of that square, I have to square root the right side. Square root of 225 is 15. So the Pythagorean theorem, while it's super important, it's not necessarily a difficult problem. You have to plug and chug. In the notes, in the handwritten notes, there is one extra example that is also listed. So again, that's there for you to go back and reference at any point, and to try it out yourself as a challenge problem.